is on. Working? Yeah, okay. So, a few things about myself. I'm working at Alcatel-Lucent as a software architect. I'm used to work over there for nearly a decade now, and I'm also working on a lot of open source software. Most of them, some of you maybe have heard about, are the OpenBricks and Geekbox projects that I've been founding, which are embedded Linux cross-built frameworks and also some multimedia HTPC distributions. Plus, also working on mPlayer, which is probably most of you know about it. So it's one of the media player application most known in Linux. So my knowledge of expertise pretty much is around open source, multimedia, and embedded systems. And at Alcatel, I'm also working on this kind of stuff. I'm also been a former speaker to different former editions of the ELCE, so mostly last year. And yeah, that's pretty much all that you need to know about me. So right now, just a few things about my job and the context of this presentation. So some of you may have used one of our products, and this is, I'll be honest with you, the only advertising slide that I will make. We have at my work in a division that is working on some IP touch phones. So this is the current brand that we have. It's a regular old school IP phones that we have for around 5 years now. And it's, you can see some hardware specifications of it. It's really running an old MEP32, really old stuff, running a VxWorks with a regular frame buffer device and really low NAND memory, NOR memory, and low, 16 megabytes of memory, this kind of thing, and you get the physical input keys. So it's really the actual, or the current brand that we have. And we were at the R&D labs actually trying to brainstorm as to what would be the next generation of IP phones that we would be able to make. So we have started some study a couple of years ago about what can be tomorrow's phone, at least for enterprise grade and not for the consumer grade. And so we have been thinking about how to design these kind of new phones with some requirements actually, as the phone has to be powered by GNU Linux and not by Android operating system. The main reason for that is because the study has been done like 2 years ago, and so Android was not that much popular and we have no visibility about it. And the idea was that the phone has to be open to next generation technologies like HTML, JavaScript, and this kind of thing. So the other parts were really remaining to our R&D imagination. So what you may expect from this presentation is actually a return of experience from this feasibility study that we have made. So for the different folks of you that just went to come here and were expecting that I give them some really nice techniques, saying, okay, with these techniques your embedded system will be twice more powerful or 10 times more powerful than it used to be, it's pretty much not the case. I'm sorry for that. For the other ones, maybe you can get some return of information and maybe a few tips and tricks that we have used internally and that were really interesting as to how to better choose your hardware and how to make some decision choice in terms of software architecture, which might make sense in some dedicated case, but not in others. So trying to find the bottlenecks of your systems and trying to enhance the different performances and ultimately not being slow by design. So as a preamble to this big presentation, I've been thinking, for the last, I now own a PC for around 20 years. So I started my schools with a regular Intel 286 desktop, and now I have this Core i5 laptop. And in 20 years, actually, my CPU, both my CPU, my memory, or my HDD got around nearly 10,000 times bigger and faster. So these are really astronomical numbers. And at the end of the day, it seems that my PC just takes more time to boot, and I just need more time to open up my regular text editor. And still, my PC is 10,000 times faster than it used to be. So at this point, my big question was that something went wrong, and I just wanted to know what. So I've set up a couple of rules as how to try to optimize your embedded systems. And the first rule would be know your hardware. This is really important for me because here are some common considerations that you may have, but knowing your hardware really is one big part of enhancing your systems. For example, you have to know that your hardware mainly for embedded systems is an SoC, so it's not just a CPU. And this may be common sense for most of you, but most of these, if you are considering some ARM CPU, most of them have some really dedicated execution modes or simply some SIMD optimizations like the SUMB, the Jazzel of the VFP or Neon stuff. And these are really interesting things that you might want to use because depending on whether you use them or not, you will see in the next slides, but this can really improve your software in a really big way. So for example, if you are intending to use Java like for Android, for example, it's really recommended to have an ARM SoC that is using Jazz instructions. Otherwise, you really are going to lose a lot of performances, and it's not worth using Java for that. Most of the high-end ARM CPUs also are featuring VFP or Neon instructions, which are really great if you are using FPU instructions. And if you are not having VFP or Neon capabilities, it's really highly recommended that you do not use any FPU routines. And so, especially for codecs management, audio or video codecs, do not use this kind of CPU. Do not use these kinds of routines. This is, however, a trade-off between the portability and the performances that you want to make. For example, if you are considering using an ARM CPU and you may, I don't know, take the latest Ubuntu stuff that you may have grabbed, they have built it for portability and not for performances. So, for example, they have built for ARM 7 and using the VFP because the Tegra chip from NVIDIA doesn't support Neon. And so for other kind of Cortex A9 chip, except from the Tegra one, you are going to lose some performances. So it's really not a good way to do. Another stuff that you can improve are the audio management. It's not really improving, but on the legacy stuff, the audio, most of the audio used to take audio decoding, encoding, and some audio filters used to take a lot of CPU time. Back to the old days when your CPU was kind of slow, it used to have some DSP dedicated to this kind of operation. Now, if you are considering some high-end ARM chips, like the Cortex A8 or A9, most of this stuff can be done in a couple, not a couple, but hundreds of megahertz or something like this. And so the trade-off between using some dedicated DSP for audio decoding or doing that in software is to be questioned because it's not really worth the case anymore. Other things that you might want to improve or just think about is the display or input optimizations. For example, you have to know what your GPU really is capable of. I mean, what kind of 2D effects or 3D effects are your GPU really capable of doing? Some are just able to draw or accelerated drawing some lines or rectangles or triangles. So these are the kind of operation that you just need to know what your hardware is capable of. Otherwise, you just fall back into software routines which are really slow, and the whole program is going to be slow with this. So this is really important to know. And another thing that is important is that your GPU is becoming really powerful, and it can draw a lot of frames per second. Sometimes, I don't know, 100 frames per second, something like this. But your LCD screen, most of the time, it's just calibrated to use, for power reasons, just calibrated to only render 30 images per second, something like this. So is it really worth having some GPU that is actually rendering 100 frames per second if the LCD just has to drop a third of them? So this is something that you can also tune, just tune the CPU or the software that you are using, not to render more frames that you need. Same goes for the touchscreen. Most of the touchscreens works with interruptions. And of course, you can just read any events from the touchscreen that you want, and you get the firmware from the touchscreen that can, I don't know, render every millisecond you can read from the touchscreen. But doing so, is it really important? Because if you're just reading from the touchscreen every millisecond, then you have to interpret the results and maybe make some move of the widgets on the screens and everything every milliseconds. And in the end, if your LCD driver only renders every 30 milliseconds, so yeah, 30 hertz, it's not really worth reading more than you can actually interpret, handle, and just display. So these are common basic sense that you might want to use. Next to that, I've done some embedded SOC comparisons. So on the left column, I just used the test case SOC that we were using on this project. And I've just also put a couple of other SoCs that you can find on the market and compared to the PC. My point with that is that from a lot of people, actually, I've heard a lot of time that the smartphones and the new tablets are going to kill the PCs, and in the next couple of years, there will be no more desktop PCs anymore. I'm pretty sure this is not true because, as you can see, actually, you just can get to see the figures, but even the high-end Cortex A9 chips are actually, if you compare in Dresden MIPS, which is not the really best comparison that you may have, but it's the less worse, even the highest chips are actually only a tenth of what a desktop PC can be. And for the SoC that we have been using, it's only 1/10 of the highest ARM chips that exist on the market. So my point with that is, for the test case SoC that we've been using, if you're comparing just the Dresden MIPS, so the raw performances of the CPU, actually it's not much, it's only worse what a Pentium Pro used to be in 1996. So my point with that is, it's the same kind of chip that was actually running 15 years ago. And so you are not meant to run the same kind of software on this kind of chip that you can run on your desktop PC right now, because this is really a big gap that happens between right now and the past. So it comes to my second rule, which is that embedded is not desktop. And what I want to focus is that it has to be programmed really differently than the desktop. So as I said, a couple of facts for that. Embedded devices are indeed getting bigger and bigger and faster every year. That's a fact. But in the end, not all manufacturers and not all products are actually using the Cortex A9 or the dual core and everything. So sometimes for shop cost reasons or something like this, you may just want to fit with some old ARM 11 or ARM 9, something like this. So they still have limited resources in terms of CPU, in terms of memory, bandwidths. They are running on batteries, they have slow IOs, this kind of thing. So they are not PCs, and that's my main point. And so why would the same kind of software run on an embedded SoC that's the one that is actually running on a PC today? And if you're just thinking about Android, the main Android just came out and diverged from GNU Linux from some reason. Most of the Android stuff were criticized by the Linux kernel guys because they are just desktop regressions. That's what they called 2 years ago. And actually, it's meant for a reason, because this Android is not meant for desktop PCs, it's meant for embedded chips. So this is really interesting and important to take into account. And I've listed just below, I just listed a couple of desktop-oriented performance-eating software and technologies. So sometimes you just go on the internet and see some new fancy software or technology that's been around, and you see there is some great abstraction framework and a messaging bus and garbage collector or virtual machine. You see XML interpreted languages and everything. This is great technologies, but these are meant for desktop. These are really not meant for embedded devices. So this can be used even better. They are even better on high-end ARM chips than they are on low-end ARM chips, obviously, but you have to use them with care, because using them are really a source of terrible difficulties. So the third rule with that is, as to enhance your performances for your device, what you need to do is isolate your system's bottleneck. Because for benchmarking and trying to understand how to improve the performances, first you have to measure. And that's one of the key points. Because measuring something is one of the highest tasks that you have to do. Because measurements must be deterministic and repeatable, because you always have to get the same scenarios, always measure the same thing, and it must be the less intrusive as possible. Because as you all know, as soon as you try to measure something, you just interfere with the behavior, and you're not really measuring exactly the same thing that when you are not measuring. Also, you have to try to cover as much scenarios as possible. So what we have done on this project is actually pretty simple. We have set up different sets of measurements. So one was to use some external approach. So actually what we did was considering some applications, which I don't know is, for example, some telephony applications that you just want to dial by name, so you have to the user has to input some name on the keyboard, and you just go on with some web services to the server just to find the user that you want, requesting some contacts on the remote server. And this can be done actually by a human. So as I said, it's just a human that is actually touching on its touch screen. Here goes to the touchscreen libraries, to the applicative framework, and goes to the application. So as to have this scenario or this measure being repeatable, what we have done is plugging some touchscreen recorder applications just over the TS library. So actually, with this way, we just have one human that is inputting some keys, and the whole thing is being tracked and recorded. So you get the exact timestamp and the exact position that you want that the user has inputted. And so with this way, we also have designed some really small remote client that can actually simulate the touch events. So we can have a lot of non-regression and integration tests that can be done automatically by some bots just simulating what the human would actually do. So yeah, it can be really fully automated like a client-server approach. And so on the other end, on the other side actually, what we have done is using this input server, we are guaranteed that the user inputs saying I want to dial this name, so I have to first dial hit this key, then this key, then this key, and this one. This is always the same kind of scenario. And so what we have done actually, instead of being intrusive and putting some probes within the software, we have been measuring the output of the LCD screen. So simply using some webcam, we just have the phone set that is being in a closed environment, and we have a webcam on it. And with the webcam, we are just fetching all the YUV frames from the given scenario. And we have some remote client on the dedicated PC that is just interpreting this video stream, and using some OpenCV libraries, we are making some computations saying, okay, this is my screen, and now we are fetching the different frames. And once the screen change, because a new widget just appears on the screen, and you get the succession of the different widgets appearing, then you can actually get one widget saying, okay, I'm now in this new state, so I can input a new key event and this kind of thing. And so we have an external approach of the whole solution, and you get to measure the solution from one end to the other without being too much intrusive on the system, except from just mimicking what the human would do, which is just inputting on the screen. So this is some really great approach as to understand and measure the different performances aspects at the user level, but the only drawback of this solution is that the accuracy depends on the capabilities of the camera that you use. So for example, if you use a 30 frame per second recording camera, obviously you won't be able to go below the 33 millisecond threshold. Of course, you can get some higher cameras, 60 FPS, or some are capable of doing much more, so you can increase the accuracy of your system when buying some much more expensive camera. Also, if you're once you have performed this kind of external benchmarking, I would say, you should be able to make some internal approach. So, for example, I don't know if you are aware of that, but the Linux kernel provides a set of tools, and in 2.6.31 and later on 2.6.32, they just added the support for the performance counter and the performance events later on. So these are the kind of successor of all-profile, and these are really using the hardware counters of your SOCs as to get a lot of information for every process. You can filter for any process, and you can filter for user space, you can filter for kernel space and this kind of thing, but you can just get the number of IRQs, the number of page miss, the number of page faults, the number of the amount of CPU time each process takes and everything. And so it's really like all profile. You can completely determine on this side it's on the kernel side, and this one on the user side. But for a given application, you can just profile the application that you want and just try to understand if there is some dedicated routines that is taking much more CPU time than it should be, and trying to find the bottlenecks. So this is one kind of approach that can be done. Another kind of approach is still when using this performance tool application that is provided with the modern Linux kernel. They have some nice application that is capable of actually recording all the performance events that go within your kernel. And so after that, you may just use on the target, you use the perf tool using the time chart record command, and then it just gets a lot of samples of your systems. And after that, on the host system, you may be able to use this data and generate some SVG file. And as you can see here, actually you have the two. You may not see much, but you get the two CPUs, and you get the time the time the CPU has spent being active, has spent being waiting for some IOs or this kind of thing. And you have the list of all the applications that are running on your system and which percent of your CPU time is consuming. So this is really interesting because you have a highly multi-threaded systems, a lot of applications are running on, and at some point you have some performance issue and you have some bottlenecks, but you just don't know why. And this kind of tool is interesting because then you know that judging by the amount of CPU taking by this kind of process, for example, this is the one that really needs to be looked at. And also it can be blocked in IOs and this kind of thing. Another thing that was interesting, if you are using, for example, Divas, maybe you can use, I'm not a big fan of this, but Divas, when badly used, you can spam a lot of messages on your system and this kind of thing. And there is some nice tool that is called Divas Monitor, which is provided with the Divas package, but also another one which is called Bustle, which the URL is just here, which allows you to have some flowcharts of all the Divas commands and messages that go through your system. So actually here you can see, you won't see the figures and everything, but you get the names of all the applications that are running, and for all the applications, all the systems that are being exchanged and the time in milliseconds between the message sent and the message received. So again, this is really interesting to understand that actually you have sent messages and it took 200 milliseconds, or I don't know how much, but quite a long time just to send the message and to receive the answer. Which goes to my fourth rule, which would be try as much as possible to kill the message bus. Really, this is something that actually we have made some framework comparison, and this is also one of the main divergence area between the Android and the GNU Linux systems, or at least the desktop GNU Linux, which is the messaging issue. So, for example, this is not a study that we've made. It has been gathered from this URL, so if you just want to have a look. So the idea was to have regular client-server applications that are doing some basic RPC call. So these were done like 10,000 calls using an old AMD system. So again, it was an old study. And just trying to send some basic RPCs, so having a void call or just having an integer as an input or output argument, this kind of thing. And they have compared different kind of mechanisms, CORBA, DCOP, and DBus. And what appears in these figures is that actually the CORBA, which is known to be quite slow, is actually 18th time faster than DBus. So DBus is really something that can cause a lot of issues to you. So more about this IPC benchmarking. So there is another thing that you may want to have a look, is a small utility program which is called IPC Performance, which is actually trying to read a number of rows. I guess by default it's 300,000 rows from an SQL database. And they have different use cases. One is having a client that just try to rows using SQLite library, just reads these 300,000 rows. And other approaches are using a client-server approach. So the client is just asking for the server to read the rows, and the server provides the information back. So using different kind of mechanisms, regular Unix sockets, or using DBus, or using DBus with a feature that has been introduced in 1.4 release, which is the file descriptor support. So the file descriptor support actually is a way for DBus to send the data over a dedicated Unix file descriptor instead of sending them over the bus. And so what you can see with this is that of the different implementation between direct Unix socket or DBus with file descriptor are pretty much the same in terms of performances. But when it goes to regular DBus, it takes a lot more time than with the other RPC mechanisms. And this is just for performances, but if you are looking for memory usage, The same goes. This is the scale for the server memory usage. This one is for the client's memory usage. And what you can see is on the server side, using either direct SQLite call for reading all these lines, or actually using Divas with file descriptor or Unix socket, takes about 5 megabytes of memory to do that. If you are using Divas, you have some high peaks over 100 megabytes of memory that is being used just to read that. So why 4 peaks is because they are read by 75K rows. So it's really important to know that using Divas, it's 20 more times more memory that is being consumed, and this is due to the fact that actually using Divas, all the data you want to send over the message are actually mallocked directly within the message, and this is not the case with the other kind of RPC implementations. So if you are going to use Divas, which most of you probably are going to do anyway, you just have to be careful, because Divas really is meant for eventing and broadcasting events, so just avoid passing data on it. And if you have to pass data, you may just want to try to alternate file descriptor usage, or you want to imagine some more straightforward alternative between two applications like regular Unix socket. And one thing that we have done also is, if you have a look at the Divas source code, well, you get the slides, but there is actually one single line of code that can be changed, which says to Divas that we trust the data that goes over the bus. So Divas, with this way, do not check for, it doesn't perform any assertion on the code, on the headers, and on the different kind of thing. And just changing these lines is actually making Divas messaging being 25% faster, which is kind of great improvement. And the next rule would be go native. Really, I mean it. So even if the phone set that we have tried to imagine has to support the different web applications and HTML, JavaScript stuff, which is really desktop trend, this is one very big key point to understand. If you have a look at actually what would be the legacy software architectures of a desktop in a few years back, I would say, you get the Linux kernel and you get the platform daemons with a couple of system libraries like the C library, and some applicative libraries that you have developed, and you have some middleware applications that you have wrote, and maybe some graphical applications also, and most of them are just talking to the system using direct function calls, or they are using some sysfiles, IPC or Unix sockets, this kind of thing. So what's good with this is that these are C++ code. It is really easy to debug. You have GDB or Valgrind or everything, so you can profile, you can debug. This is really wonderful. But on the other hand, if you are going for applications portability or scalability, easiness of deployment and everything, this is maybe not the best way to do things, but it's a trade-off. On the other hand, if you are just looking for desktop software architecture comparison, this is pretty much more what currently looks like a modern desktop. So you still have the Linux kernel, and you still have the platform daemons and the different respective system libraries and application libraries. But on the other hand, you still have applications on top of that. But what you can see is the more often you get the message bus that goes in, and the different applications are not talking directly as we have seen, but they are talking with message bus, and so they are serializing a lot of data and deserializing this data. So it takes a lot of CPU time, and most of the time you also get a web browser which is running web applications in an interpreted language, which is HTML and JavaScript, and you get also one more layer of serialization which goes with the JSON and everything, and you get some native browser plugin which actually are developed in C++ because you just want to have performances in your web browser and your web applications. So this is the modern trend of the desktop, and of course it's easy and fast to write, so everybody can say, okay, I'm writing some web applications, this is quite easy, I'm using some CSS and everything, and makes the skin look better, and it's really easy to do. But at the end of the day, for those who have already developed some web applications, you might see that it's actually interpreted and compiled in time, so necessarily it's much more slower than any native application would be. And it's really, really hard and sometimes impossible to debug. You have a lot of memory leaks, and you really don't know who allocates the memory, who deallocates the memory. You have cross-references everywhere, and it's really, really hard to make. But again, trade-off has to be made whether you want a high portability of your applications or if you want to have real performances. And what's really interesting to me is that actually what you can see is today, I personally see the web browser as some kind of virtualized operating system running in another operating system. So for example, you are taking the Google Chrome or something like this. If some of you already had a look at the Google Chrome sources, or the Chromium sources at least, because Google Chrome is proprietary, you can see that actually the web browser is some kind of mini operating system in itself. It has a lot of libraries included. It has some JavaScript interpreter. It has some web page renderer. It has some HTML parser, XML parser. You get some scheduler, some memory allocator, some process monitor, because every tab is running in a dedicated process. So it's really some kind of mini operating system with some kind of abstraction layer. And in the end, what it does is calling native applications either directly through the browser or through dedicated plugins that you are able to write. But in the end, it doesn't do more than what your regular native application used to make. The only thing is that now you are able to do that in web applications. So you just have added a lot of other layers and layers over layers and layers over layers just to write some web applications, but in the end it's really not doing anything more than what you could have done with native applications. So for that, the HTML5 is kind of better because it's just removed the message bus and this kind of thing, because you are just making some bindings between the JavaScript and HTML thing that is on top of the browser and the system libraries that are below. And so HTML5 is actually doing a lot of stuff within the browser, but it just puts all the complexity in the browser instead of putting it in the operating system. But in the end, it's just one other framework, being the browser. So my point is that now the modern browsers are actually to JavaScript what the POSIX convention used to be for C. It's just one way for web application developers to make some somehow portable applications, but in the end, all the complexity that used to be done in the operating system now is being done in the browser. So the work remains the same, the performances have decreased, but it's just another kind of people or another kind of place that you have to do the work. So in conclusion to this slides, I want to remain the 5 rules that I've been able to isolate. So really know your hardware, and knowing that embedded is not a desktop, and also you have to isolate your system bottlenecks and kill the message bus to go native. This is really my main points. So again, in conclusion, I would say that your SoC never has been powerful, but really it's not a reason to waste any CPU cycles, and it's not because it's powerful that you have to write JavaScript things that you could have done in a native way. And again, this is some kind of recommendation, but it isn't for embedded. It really is not desktop. So do not try to follow the same software development techniques. And if you just have a look at Android, it really differs from GNU Linux, and not just because of Java. It's really a completely different approach in terms of resources management and everything, and it really makes sense not to use the desktop approach for doing this kind of applications. And again, you have to go back to the basics, because it's really, maybe in schools lately, it's all the people are just taught how to learn to build web applications in HTML and JavaScript and everything, but it's not that much easier, and you could also do that just in regular C and C++. And so as we still have a couple of minutes, I'm just trying to point out to you a couple of backup slides with the miscellaneous tips and tricks that we have actually made on our project. So this was really interesting stuff. So an example of that is, for example, the data serialization that we have talked about. So again, this is something that really consumes a lot of CPU time. So by all means, if you can avoid any data serialization, just do it. So avoid using some memory bus and this kind of thing. And if you really have to do some data serialization, just do not use, I don't know, the Qt stuff that can be implemented for you, where you just send over the whole objects from one application to the other. Just think carefully what are the real important elements that you want to serialize, because every time you do that, it just takes a lot of CPU times. For example, still using the JSON thing, we have taken some open source software called QJSON, which is a binding between JSON and Qt framework. And actually, what the thing does is just converting some binary objects from Qt into some strings in JSON. And what it does is simply, it does its job, but it also adds a lot of things that are completely useless. For example, between every braces in the JSON thing, it just adds some spaces. So this is really great when you are using Wireshark, because you see a better indentation. But for your processor, it's just more strings and more characters that it has to handle, and it's really not worth doing that. Also, and this is something that I've seen in many programs, the log issues is really important, because most of you probably have, it's pretty much unreadable, but you get the slides on the internet after that. But for the different logs mechanisms, most of you probably use some macros with some debug level for the logs, whether or not they are to be displayed. And in many programs that I've seen, actually the string that has to be outputted is computed before the log level being checked. And this is a really stupid idea, because every time you want to compute strings, well, it's also some kind of CPU time that is being consumed, and it's really not worth doing so. Other kind of things that you want to do is regarding memory allocations. This is really going back to the basics, but again, you have to avoid any kind of memory fragmentations. The kernel is just waiting a lot of time every time you just requesting mallocing some memory, just trying to fetch some pages, and depending on the size, it's pretty much slower operation. So if you have some memory that is available, you may just want to keep the objects in memory as long as you can, and try not to alloc and dealloc them continuously, because you're just increasing the fragmentation. Also, in terms of performances, if you are really meaning to have some low latencies and this kind of stuff, then you may just want to go back to the real-time usage, which was to have some kind of dedicated memory pool, so that once the application just starts, you just allocate some big memory buffer, and you just have your own memory allocator within this buffer. And so there is no malloc anymore, no free anymore, and you just avoid any fragmentation, and the whole thing is much faster to use. Also, some compiler optimizations that you can use. Of course, most of you can probably know that, but GCC can do wonders by adding different optimization flags. So again, it depends whether you want portability or performances, but you may just simply specify which architecture you are building for, and using different levels of optimizations, specifying the usage of Neon optimization or ARM chips that supports it. And of course, if you are using some Neon code, one good thing would be to, if you have the knowledge to do that, to just write the Neon instructions yourselves. So for example, this is some sources of a really small benchmark that I took, and I just made some comparisons with GCC, and using some regular optimization, using some optimizations for Neon, and using inline Neon assembly code that has been written. And you can actually see that executing this program on I think it was on a Panda board, the scale of performances goes from 1 to 10, whether you are actually using this kind of optimized instruction or not. And this is really a great improvement. And what can be done with that also is use some software that is named Acovia. With this kind of software, actually, it's a software that uses some evolutionary algorithms, and you just isolate part of your program that you think is relevant in terms of performances, because you are using it a lot of times, and you just isolate it into one single C file, and you run Acovia on it. And Acovia actually tries to use as much optimization, compiler optimization as possible, and it just tries to then to run the code and to check what are the best possible GCC optimization that you might want to have if you want performances, or if you want code size, this kind of thing. But it just runs all the optimization that GCC has, it runs for you, and you just get to know what's the best for you. Another thing, if you really, after this presentation, if you're still really convinced that the web application trend is the way to go, well, it's up to you, but it's this way. We still have used some web technology stuff in our product, and we have still made a lot of improvements over the different web engines, or simply on the CSS. For example, on the web engine, if you have just-in-time support, just use it. It's really worth it. And we also have made a lot of hacks directly within WebKit, which we were using, because there were a couple of widgets which were invisible to the human eye, which were actually out of the screen boundaries, or they were simply in a below layer, this kind of thing. And even with that, WebKit used to render them. So they were not displayed on the screen, but the rendering routines were called, and the CPU was consumed to actually render widgets that do not appear. So it's pretty much useless. And also, when using WebKit on any embedded devices, you have to limit the cache for the CSS, for the files, for everything, because otherwise the whole process gets really overloaded, and you get on free memory. And again, it's really complicated for the kernel because it has less free pages, and so it makes the whole system being much slower. Another thing that you can do is actually to simplify your CSS if you are using some web applications. So avoid any CSS transformation as possible, and use really simple CSS. For example, using CSS gradients on some widgets instead took on our CPU, we had some scroll list with some widgets, and each widget has some CSS gradients. And just scrolling within this list have 90% CPU usage. When we just replace the CSS and use, instead of the gradients, just use a solid plain pattern, just one color, then the CPU usage falls down to 3%. So even as simple as this could be, this is really completely changing the way the software was running. And one other thing also is if you have some application that is actually meant to run on one specific hardware with one specific screen size and everything, just prepare your images or button images for widgets and everything to have the correct size that they are going to be displayed on. Otherwise, again, it's just some waste of CPU cycles just trying to resample everything in software. And again, still, if you are going to go with CSS and JavaScript and everything, try to reduce the HTML file as much as possible. It's quite often that HTML pages have up to 20 or 30 levels of depth, which is quite a lot of information to process. And also, if you are using some web services, maybe it's the right thing to just ask for a call of some web services that fetches the most information that you can, instead of doing as much web services that you would do that provides a lot of information every time. And also try not to refresh the MMI as often as possible. Refreshing the MMI, rendering every widget in HTML and everything is really quite a slow operation. So just wait for all the data to be there, and once everything is there, just refresh the MMI once. This is really something that's fast on everything. And if you're really interested in the JavaScript, there was some conference at O'Reilly's about how to make JavaScript fast, or at least how not to make JavaScript slow again. So if you're really interested in this kind of technology, you get the URL of this kind of presentation. And again, this is really my final conclusion for that. As much as possible, use native code and put all the logic that you could do. Use C and C++ for that. Use HTML5 native plugins for your browser whenever you can. It may be boring because it's C and C++. It's not the current trend of doing JavaScript and everything. But if you really want to go this way and have some really good performances, just write native code. Okay, that's pretty much all about it. So I really hope that you have some better understanding of what to do and especially what not to do with embedded systems, and that they are not desktop and they really can't be programmed the same way. So thank you very much for your attention, and all have a good lunch.